So I am going to start the recording. You should get a little notice about that. And I am going to start, and people can join us as they will. Just sort of looking at faces. By the way, I do have two screens, which is why if I'm looking to the side sometimes is because I'm looking at all of you. But just sort of introductions, I will just say briefly, Morgan and Dietrich are my grad students who are working with these methods. Dietrich's going to be working with it in mine waters, and Morgan is kind of getting pressed into service because she has really good lab skills. So we're going to take full advantage of her and have her help out on some of this project as well, with cleaning up some stuff. Camille is a PhD student at University of Pittsburgh. I assume Brian and Rosemary couldn't make it today, Camille? I never heard back from them, but it happens.
Yeah, I never heard back about that either, but.
Well, since we're recording, I'll share it with them and they can decide. Ellen Herman is at Bucknell, and there's actually some data of hers in here. She's also been pursuing this with Hank Edenborn, and Janet Herman, geochemist, retired from UVA. And many of you have seen her data. If you've taken my class, you've seen her beautiful data over the Travertine waterfalls in Virginia, which we use for all kinds of things in aqueous examples and exams and problem sets and such. And I invited Janet particularly because it's good to have another geochemist helping me think all these things through. It's you know, Janet is Janet. And Janet and Ellen are not related, for those of you who haven't met them before. I'll just get that out there. Okay.
Just academically.
Just academically. We are all Will White connected in this process. And Ben, I almost forgot you. How could I do that? Ben is a recent PhD graduate at the University of Pittsburgh and is running Head in Environmental these days and is doing this kind of work for research and consulting, and did some for his PhD, and is generally just interested in CO2 also in mine water as someone who builds a lot of passive treatment systems. Okay, so I put this together. This was actually enormously helpful for me to put together this talk because I'm working on a paper right now, and you'll sort of see what where I've been challenged and what's working and what isn't working. But I realized in doing this, I kind of have to take everyone through the whole process. Now, for some of you, this is all new. Some of you have been working with this, but I realized that I haven't always done a great job communicating what we do and why we do it to everyone on this project. We just sort of send students out with, here, this is how it works, go get data. So I'm going to kind of go through the whole process. This is really big picture-ish, and I apologize if it's going to be a little long. The slides tend to have a lot of stuff on them, and I'm not going to cover everything on the slides, which is part of the reason I'm recording it, and you can have the slides to go back to as well if that's of interest to you. Okay, so sort of big picture, some other ways people do this, field methods, work through the whole thing. This picture here is at Iron Falls on the Occoquan River. You can see the CarboQC is busy out there collecting data at an acid mine drainage site, which is one of the things it does really nicely for us. Okay, let's go to where I can forward. Okay, so I got drugged into this whole thing by Hank Edenborn, who is a microbiologist at NETL, not NEL. And Hank and I were working on some CO2 analog questions and really needed a better way to measure CO2. And we wanted field methods and lab methods. And we were particularly looking at some of these acid mine drainage sites, and I'll explain why they are a real challenge in this. We're interested in sensors. The sensors on the market were just sort of starting to come out then, or there were some out, but there's issues with sensors as well. So this goes back to about 2008 when we started, and you can see Hank at his feet there is the CarboQC out in a woodland site in this case. You know those websites and those people who steal little garden gnomes and they take pictures of garden gnomes in all these different places all over the world? I realize that's kind of what I've been doing with the CarboQC. I could have like a whole slideshow of CarboQC in the field going places. Yeah, you'll see lots of them. Okay, so some of you know this backwards and forwards. Some of you know it not as backwards and forwards, but just a quick review on DIC, that's dissolved inorganic carbon. If we look at the mass balance on DIC, it's the sum of 3 different carbonate species, H2CO3 star, bicarbonate, and the carbonate ion. And that H2CO3 star indicates that this is both dissolved CO2, that is carbonic acid, and also dissolved CO2. Janet, I'm going to try hard not to call it a dissolved gas today. Janet and I had various emails about this yesterday. The other thing on this figure, so you can see, and I think all of you are well aware of this, this is the plot of the speciation of the carbonate system over pH, and our species depends on what pH we're at, but the total DIC is constant regardless of what species are present. The big blue arrow here is to point out that the H2CO3 star, although it is both carbonic acid and dissolved CO2, it's almost completely dissolved CO2. So if you just look at the scaling, this has true H2CO3 on this plot. This one is from Stum and Morgan, I believe. And that's orders of magnitude less. So that's 3 orders of magnitude less than what's actually dissolved CO2. So when we talk about H2CO3 star, it's very reasonable to assume that what we're really talking about is dissolved CO2, which is what we are interested in. So that works quite nicely for us. And I also remind us that there's a whole list of different ways we can get into the carbonate system, whether it's pH and DIC, but we can look at any of the different species. And if I know any 2 of those, I know all of them. If I think of systems of equations and variables, like I said, I only need to know 2 and I know them all. And this turns out to be really helpful for us. There are some adjustments we'll want to make for temperature and ionic strength, but those are of lesser impact than being able to calculate these values, figuring out 2. This gets utilized to back calculate CO2 all the time in data sets. Again, specifics to come. And if you've never seen this paper, and my guess is Janet's probably the one most likely to have seen this paper in the past, just because it's such a really fun little classic of carbonate geochemistry going back to 1965. This clever person put together these contour plots in which what you do on the x-axis is you plot total DIC in millimolar, and then you plot total alkalinity on the y-axis as milliequivalents per liter. And you can go to different contour plots and determine pH, negative log of the CO3, the bicarbonate, or the negative log of the CO2. And I always really kind of like this. I thought it was a nice, clever graphical solution. Fortunately, now we have Excel and Mintech and Freak and much easier ways to do this. But I always thought this was a very clever example, but it's also a good example of saying if we know any 2, then we know all 3. You can also use the contours on this to back determine what axis you're on. So if say you knew the pH, you could take the pH and the alkalinity and figure out the total DIC from the contour too. Anyway, it's a clever little paper. If anybody wants a copy, I'm happy to share. Okay, so how do we go about this? We're going to use this if we know 2, we know them all approach. And the first thing, the way people determine CO2 in waters is to back calculate it based on that carbonate chemistry, assuming we've measured alkalinity and pH. And this is the basic equation. And we find this in lots of textbooks and all the karst textbooks. It's been used extensively in karst. And the nice thing is you can get your alkalinity and your pH using field meters. So you can calculate a lot of this data purely just knowing or just having field equipment. There's a couple issues for me in this. One is it does assume that all carbonate is, or all alkalinity is carbonate alkalinity. Now that's a reasonable assumption in most waters. It's certainly a good assumption in karst. But sometimes we do have non-carbonate alkalinity, and the issue is more if we have non-carbonate alkalinity, but it's unknown. So we don't know if it's there or not. The other really big issue here is that it requires us to have measurable alkalinity. So that means any sample with a low enough pH not to have measurable alkalinity, we're not going to include it in this. And we see this over and over again where people do estimates on larger scales. So this way you can sort of back project it and predict it. But given the errors in both alkalinity and pH, I think that I always wonder about that a little bit. And really, as we all know, if I have a whole lot of CO2 in my system, I should have a low pH. So this ends up ruling out a lot of samples. And just a note on that. So again, we see this done a great deal in karst settings, and it works great in karst settings because our alkalinity is carbonate alkalinity. We're at a good pH that we have measurable alkalinity. There's enough alkalinity there that we can get a pretty good measurement on a titration. And one of the things we see is if you look back at published studies where people have looked at CO2 evasion studies. So there was one, I want to say Butler, I think. I didn't write down the reference, but one of the big papers that looked at terrestrial evasion of CO2 at a nationwide level, basically, that's what they did. They went back into the USGS database where there's lots and lots of alkalinity data, and they used alkalinity data. But that, of course, is then going to skip all the samples in which there's no measurable alkalinity. You can see the growing issue of why we have a problem with mine waters. Okay, so the other issue and the other sort of standard method in which people determine CO2 is you measure dissolved inorganic carbon in the pH, and we do a mass balance and can calculate the CO2 concentration from that. Again, we know any two, we can calculate all the others. So this is pretty standard as well, and this works very nicely at low pH. We can still calculate low or CO2 from this approach. However, most of the analytical equipment isn't really designed to handle this. So there's a whole series of equipment. I think it's Siever's system that's used for measuring TOC, total organic carbon, in drinking water. And they really, when you put a high DIC sample in, the whole thing just sort of falls apart. It doesn't work very well. One of the most common instruments people use for measuring DIC is a Shimatsu. And the Shimatsu TOCV system, what you do is you take your water sample, you combust it over resin, and you measure the CO2 that's evolved from that combustion process. That's measured with an NDIR detector, and you get a nice DIC concentration on that. Well, we have a couple issues. And one is if we have very high PCO2 samples, our bottles often leak CO2. They're not designed to handle CO2, Nalgene, and certainly not the bottles that you put on your Shimatsu auto analyzer. They do not do a good job keeping CO2 in. And the other is, as part of the QC process on that instrument, it takes a first pull out of the sample vial to flush the lines, and then it takes 3 additional pulls, possibly 4, until it gets an answer that matches the standard deviation that you have set as your criteria. We see consistently that each one of those 4 pools, the first one is always higher in CO2. So when we have a very high CO2 sample, it's degassing rapidly enough that those multiple pools, we absolutely see a consistent difference in each step. Okay, so our 2 standard methods, they work sometimes, but I'm not sure they work in the settings we're interested in these mine waters. Okay, so then Hank and crew, we were looking at field meters, and we did a lot of sort of reviewing what was out there. And this again was back 2008, which is a little bit earlier. And one of the things we discovered, the NDIR detectors tend to be to measure gas. So maybe you take your gas probe and you put a sleeve over it, which is CO2 permeable, but not water permeable. So it stays dry and measures CO2. But there are issues with time of response. There are issues with clogging of the membrane, issues with barometric pressures. So there are a number of different things that end up being problems with them. You can get great data. You can get good data through time because they often have data loggers, but there are some complications of those. The other thing we found in looking for equipment is there's this real dichotomy between the environmental world and the industry world as far as what they like to produce. So we would talk to the people in the environmental world and say, this is the CO2 we're interested in. And they're like, oh, that's going to blow out our system. So the CO2 we have in the mine waters is enough higher than what people typically see in environmental systems that the stuff that was designed for environmental systems didn't work very well at that time. Things are improving. We talked to the industry people, and they could certainly handle measuring high CO2 in water samples. But when we said I wanted to take it out into the woods and set it up by a creek, they thought we were crazy. So there was this sort of disconnect between what we needed to do and what was out there. This particular figure comes to us. Thank you, Ellen. I did find the file eventually. And this is some more recent data logger data. And Ellen will have to answer this in gory detail for you, but she and Hank got involved on a project as well because Hank's out there just recruiting people who will do field work with him. And they put different kinds of sensors in different locations. And this is from a karst spring, and it has both a C-sense and a Vasala sensor. And you can see just on the graph here, the red is the Vasala, the black is the C-sense. And the trends are certainly the same, but we have very different level of detail in these two. And I'm not going to try to explain this right now. You can talk to Ellen later since we have her here. But I just want to say we do need to be careful with the probes by all means. This was a great little GSA poster done by an undergrad who worked with Ellen, Maddie Fink. And we keep going back to it, and I keep using it in various publications, not publications, but presentations at this point. Okay, so the field sensors weren't fabulous. We were having problems finding things. Actually, an intern who was working for Hank at the time spent a whole lot of time on the web looking for instruments that were out of particularly we started thinking we should look at the beverage industry. And we found this little baby called the CarboQC, and it's built for the beverage industry. It's used by bottling plants. It's also used by breweries. And the nice thing is it's hardy because it was designed to be carried around on the brewery floor and just sort of attached to large tanks on the brewery floor. So it looked like it could be portable. It was rugged enough for us, and it measured CO2. It doesn't measure a lot of environmental CO2 concentrations that are too low. So it doesn't have that really low level sensitivity, but it does get us to what we need with these mine waters. So when we measure CO2 on this, it gives you CO2, it gives you something called air, and it gives you temperature. Now, what exactly air is, we've been told it's all the other gases. And that's the most we can get out of Anton Parr on this. We've tried to work this through, but I think it's just anything else that isn't CO2, and they've never really bothered to spend a lot of time on this. There are different settings on the instrument. We use a mineral water setting. It turns out there are separate settings for cola, for Coke and Diet Coke, because fake sugar and real sugar in solution create very different solubilities of CO2, which I always thought was kind of interesting. Okay, so basics on how this little guy works. It is based on the principle that CO2 is more soluble than most other gases in our environmental samples or in air. So here is my bottle. You can see the upper bar plot is in the airspace, and the lower one is in the liquid. And you can see that oxygen and nitrogen are primarily in that small headspace, whereas CO2 stays in solution. So it's this difference in solubilities is what they take advantage of. The way it works is there's a small chamber. If I go back one, oh, you can't see it, but I have better pictures coming. There's a small chamber on the top of the CO2, and that expands twice. And while the expansion happens, temperature and pressure are monitored in that little chamber, and then ideal gas law is used to determine the pressures of CO2. And the math is there. This is actually out of the presentation we finally drug out of the Anton Parr people to work through the details of exactly what it was doing. But it works pretty well for our purposes and what we need. If you just want to see how it works, here is our CarboQC. This is a funny little video on YouTube where they just show you how it works, so you can see the process. And this was something for the soda industry. So I've got the link there, and I will share slides later if people really want to go watch it. It's kind of funny. The music always makes me laugh. It's very dramatic. Okay, so then the question is, do we have any other soluble gases that are more soluble that are going to cause a problem with our samples? And it turns out the one gas that we do see in the environment, which is more soluble than CO2, is hydrogen sulfide. We don't see this a great deal in our field sites, but we do sometimes see it. So the one on the left is Cesspool Cave in Monroe County. That milky sheen are the sulfur oxidizers on the surface of the water because we have so much hydrogen sulfide coming out of the cave. That's why it's named cesspool. It has that smell. And in the right, this is Jefferson Pools in Warm Springs, Virginia. And this is just, again, that milky sheen coming out of the Jefferson Pools. The good thing is, so we've gone back, done the calculations, and it turns out with hydrogen sulfide, the odor and safety thresholds are much lower than when we would get interference from CarboQC. So we are not going to see this as a common problem, certainly not places I work, because once we start smelling H2S, we get out of there. We're not going to go sampling in those sites. However, Hank Edenborn has done some work in oil fields, and in an oil field, and when you're sampling at a commercial oil field, you do in fact sometimes have very high CO2 where it's a problem. And he came up with this clever solution. Hank's now retired, but he's trying to convince me I need to write this up and publish it. But it's a nice little solution where he takes a bottle and he fixes it with a certain amount of solid carbon sulfur, or he adds copper sulfate to it. So this is a freshwater sample. The bottle on the left is just a sample. The bottom on the right has had copper sulfate added. In this case, there aren't any sulfides present. So what happens is that copper ends up just turning blue. So you've got this nice blue bottle, and it indicates we have no sulfides present, which is all very nice. But if you compare that to a bottle from the oil field where sulfides are present, we precipitate out copper sulfides, which are pretty insoluble, and they turn black. So now we've done two things. One is that bottle turns black, and so I know the water contains sulfide, but what we've done is taken the sulfides and converted them into a solid form in the bottom. And I can actually analyze this directly on the CarboQC and get the answer for CO2 without a sulfide interference. So this was sort of something Hank was playing with. He's done, I think, a meeting poster on it, but it hasn't ever gotten around to publishing it out. But it's a very nice technique. But I'm not going to worry about it too much because I don't want to go sampling places with lots of sulfides. Okay, so yeah, we take this thing out all kinds of different places. There's Hank in the lower right, That's at a spring in Monroe County. Joe Rydell doing her master's on the left, working on the Youghiogheny River. It is nicely portable. It fits in a backpack. We've hauled it places where you've got to climb up hills and you need your hands. So if we go back to the lab, one of the things we need to do is we'd like to be able to analyze more in the lab, but we also need to be able to do something with standards. So in this video, one of the devices, the CarboQC was the little guy on the left, but there was this larger device on the right. And this is a pressurized filling device, or what Anton Parr calls the PFD. So the reason the PFD is used is you can put your container in there and it's under nitrogen pressure, and it transfers the sample to the CarboQC under nitrogen pressure, so it does not degas. So one of the issues you might have is if I just took a water sample that was really, really high in CO2, or I try to take a soda sample and put it directly in the CarboQC, it will degas in the infill line before it actually gets into the chamber. So we want to use the PFD for more field samples, and it turns out this worked pretty well. We could use soda bottles, not Nalgene, and not Voa vials. So the figure on the right, the Nalgene bottle is on the left. So I'm just looking at these two little bottles on the right with the big X through them because we don't like to use them for this. The left one, Nalgene, just isn't designed to keep CO2 in very well. The one on the right is a Voa vial, which is designed to keep volatiles in. It has a septum cap. However, it does not keep CO2 in very well. Initially, this didn't make sense for me because, gosh, it was designed for volatiles, to keep volatiles in. However, when we sample volatiles in this, they are typically organic contaminants, and they're there at very low pressures. But when I put CO2 in, it's there at a very high pressure. So sometimes these keep CO2 in reasonably well, and we've even changed to a sturdier membrane on them, but you can't count on it doing that job. On the other hand, Coke and Pepsi have helped us out tremendously because they have spent clearly a lot of research time and money developing a bottle which keeps CO2 in really well. So we take advantage of that and use bottles that are used bottles from Coke and Pepsi. We do, after we put the cap on, we seal that with electrical tape to get a better seal, and they keep CO2 in very, very nicely, particularly compared with Nalgene. Okay, so early on in this process, we needed to create some standards, right? We wanted to be able to test these methods we were developing. And it turns out, if you want to create a CO2 standard, you'd think it's very straightforward, but maybe not so much. And the first thing we do is said, well, do we need to mix gases and then add gas to our sample? And then we can measure the pressure at equilibrium in our system. And I started thinking about gas manifolds and mixing devices in my lab. And I thought, oh, no way. I mean, some people, however, are crazy enough to create these in the field and mix gas under different partial pressures, but they also have extra support from the people at Airgas helping them out to do that and to build those manifolds. I didn't want to do that. So, okay, that's out. So we said, what's the next thing? Oh, this is really easy. We take a sample with DIC and we add acid to it. Well, we add acid to it, it converts to CO2, and then we can measure the CO2. So all we really need to do is create DIC standards and add acid, right? I presume you've all seen this video somewhere along the way from the EpiBird people. This is kind of what happens when you just take a sample with high DIC and try to pipette a bunch of acid into it. Fortunately, this largely happened in the hood. Dorothy getting completely sprayed with CO2 everywhere, and Hank just laughing hysterically and sorry he didn't get his phone out ahead of time so he could take photos, because we attempted the EpiBird experiment in his lab. Okay, so that's out. So the next thing we could do is I can go to Anton Parr and buy some calibration standards, and they create these calibration standards that then you can just put in your sample and test your CarboQC. 3 of these cost almost $500, and you get 1 concentration of CO2 in them. So this isn't going to work because we've done hundreds and hundreds of samples for standards. So it's not flexible enough, doesn't really work. Occasionally it's useful to check calibration, but isn't going to work for us on a regular basis. Okay, so where we head next? So what we decided we could do is if we had a buffer that controlled ionic strength and pH, and we could mix that with our sample in some sort of a controlled setting, this would work. This is the buffer we ended up using. We can make this, but we find the purchased ones, we get a more consistent product. I don't know why we can't make it as the same quality. but this is called an ISA. It's an ionic strength adjuster. And this is made by Orion, and it uses a HEPES buffer, and it's got a pH of about 4.5. So what it will do is it will bring the pH down low enough to convert the DIC into CO2, but just down to that. I'm not going to outrageously low pHs. So Hank sort of came up with this system in which we use that buffer. So I take a big syringe, and I typically fill it underwater, or I fill it with my DIC standard in the lab with 100 mils of sample. And then I fill a small syringe with 10 mils of my buffer. I connect them with a small piece of tubing. They have lure locks on both ends, so it's well connected. And I basically inject my ISA into the syringe, and this is all sort of done in this contained little system, so it works pretty well. I mix my syringe well, and now I have a mixture in which I've converted most of the DIC into CO2. We can do this in the field. That's a nice thing. We take the Orion buffer, we take our syringes and our connectors and everything, and it works very nicely out in the field as well as for standards in the lab. To do the calculation from this, there's a couple things we needed to consider, and it's based just on the mass balance of DIC. And this equation here, all this is the mass balance, where the first term is the H2CO3. The next term is the bicarbonate. The third term is the carbonate ion. That 1.1 at the end is the dilution factor that accounts for the addition of the buffer. So it's 10 mils of buffer to 100 mils of sample. Yeah, I'm assuming conservative mixing here, but I think it works out okay, even though the buffer is clearly much denser than the sample. So one of the factors in this that took us a while to sort out is that the CarboQC is truly giving us an activity, a CO2, not a concentration, but an activity. And I say that because it's a process, it's a degassing process. So it's a reactivity, not just a mass calculation. So we do have to correct for that activity concentration using these gammas, or the activity coefficients in the process. We also assume that what it's measuring is all dissolved CO2. It's not carbonic acid, which, as I explained earlier, I think is a pretty fair movement. So this works pretty nicely for us. We can create standards this way. We did this first for the first publication Hank and I did on this, which was just the CO2. I've referenced the DIC method here because that's where this whole derivation is included, but the CO2 method to create the standards, we also use the same approach. Now, there are a couple of advantages to doing it this way. And because I'm using that buffer and it's an ionic strength adjuster, I fix the ionic strength in all of my samples. And because I'm fixing the ionic strength, I can use the same activity coefficients for everything. That is all samples, not for all species, but all samples. And these are the correction factors, or the activity coefficients we use. They mostly, what we did is a lot of modeling in MinTech and FreakC, just looking at what the average values of that should be, and said, well, it's a very small range and there's very little error created by changing those numbers. And therefore we're not going to worry about them. We're going to just fix them and say, okay, that works. And it's because we're using this constant ionic strength solution. And we do also correct K1 and K2 for temperature, and I use the Plummer and Busenberg correction for that. Okay. So overall, it works pretty well. So these are just our comparisons where I have my CO2 calculated. That's my known value on the x-axis. It's calculated because my known is DIC, and my CO2 measured on the y-axis. And you can see these curves are mostly pretty good. This is the same curve. It's just I've blown up the 0 to 4 on the axes on the right. So we have a little bit of a low bias on the lower concentrations. Okay, so we felt like we could create standards pretty well in this process. That's actually a pretty big range of dissolved CO2. The one on the right is probably closer to what we see in natural systems, but we do have some mines that are pretty high. So we wanted to run this up to a reasonably high CO2 millimolar concentration. Okay, so that's where we started. This is all the field stuff, and there's the 2 publications on that with Hank and I, one being just CO2 and the other one being the DIC full method. Okay, and what do we learn in all those? This is out of one of those papers. And I just point out on the left, we have mine drainage karst, thermal mineral waters. The one to the right is, I think, the one to the left, Karst, is actually tufa. And the important points on here that I want to mention, blank samples. When I run blank samples, that's that solid bold line. So I've given you some horizontal lines. So that's what a blank looks like with my tap water. The dashed line below it is the equilibrium with the atmosphere. So if a sample is purely at equilibrium with the atmosphere, it's probably below my detection. That 0.14 is our statistical method detection limit. So we did a method detection limit study, and that was the number we came out with for our detection limit. And that's okay, because most of our samples are above that, and we're more interested in these higher value concentrations. Okay. So again, this isn't going to work at atmospheric equilibrium, and I do need to account for that method detection limit in my lower CO2 samples. All those other data sets, I can go back to the publication. If people are interested, I can share that if you don't have it, because I'm sure all of you have read it very closely. But those are everything from CO2 storage sites to natural waters. We started looking more and more at field data and where things are on this. So these are just pH versus dissolved CO2 at lots of different sites. The ones I want to point out here, Lambert's Run is one we've worked at it quite a bit, which is the big blue dots. Irwin Basin, that's where Camille is working these days. This is older data. In fact, Ben, you were along the day we had like 15 people for 10 hours and we went to every single site with a lot of people. That was the data we collected that day. So that gives you an idea of what the dissolved CO2 and pH are like in the Irwin Basin. Good stuff, huh, Camille? That's your baby. Yeah, Wingfield Pines. Unfortunately, the folks who were working there weren't able to join us today, but they were some of the people who were asked that I record this. So Wingfield's Pines, in fact, Ben, you guys built that site, didn't you? Yeah, it's also got a pretty fairly high CO2. We don't have a lot of data from there because right about the time we started collecting data ourselves was the same time in which it blew out and we weren't able to continue collecting. Couple things to notice, I've put lines on here, 4.5 and 6.3 are the PK1 and PK2 for the carbonate system. So the samples below 4.5 really don't have any measurable alkalinity, but some of them do have a reasonable amount of CO2. And we do see that the Irwin Basin is a great place to see that. Also, from the same day out there in the Irwin Basin, data that Ben and I helped collect, if we look, these are moving down the basin. So most of you probably don't know much about this basin. It is a coal mine basin up in the Pittsburgh area. It's a synclinal structure. And the cool thing about the Irwin Basin is that we can see the evolution of mine water from the recharge area further down to where it becomes a deeper flow system, and the chemistry has developed quite a bit. So here from on the x-axis, we're working our way down the basin. We're at 0.0, and these are just ordered in the direction down basin. But when we start, we have we have a low pH, and all of our water all of our DIC is pretty much in the CO2 form. And as we move down through the basin, our pH goes up, and the difference between the CO2 and the DIC concentrations change over time. Part of that is, in fact, the increase in pH. That is, we are converting CO2 into the bicarbonate. Well, that shouldn't affect the DIC. The other is we are generating alkalinity and dissolving additional carbonate as we move our way downstream. And you can see the EH becoming more and more reducing as we work our way through. This is Camille's dissertation in one shot, right? No, she's got a lot she's working on out there right now. Okay. We also are interested in how consistent are these numbers through time. So Wingfield Pines, the few data points we have are pretty consistent. Dan Harris has agreed to start collecting data out there on sort of a monthly basis for us once we get those models made. Lambert's Run, you'll see there's that one low point is really kind of concerning, right? So Kyle collected that data point, he went out the next day and collected more, and he went out the next day and collected more, and it's real. So one of the things about Lambert's Basin is we couldn't sort out why is the CO2 so variable, and that was basically the main topic in Matt Bell's thesis. and he sorted it out. It's actually a switch in the hydrology of the system. There is an air shaft upstream, and when the rain's hard enough that we're getting injection of rainwater through the air shaft, we bring the CO2 way down. So there's a whole thesis on that point, it turns out. Very nicely done by Matt. Okay, so moving forward, we wanted to be able to measure these things in the lab. So it's all very well for us to go out with our one CarboQC, but it was getting older, the battery was getting iffier. But we also wanted to be able to collect data from more sites. And I wanted to be able to give bottles to people like Dan and Ben and say, yeah, collect, bring them in, we'll analyze them for you. So for CO2, this was pretty straightforward. We went with our soda bottle approach. People could fill their soda bottles in the field, wrap them up with electrical tape and bring them back. So for CO2, we've liked that pretty well. So you might ask yourself, how well do these bottles hold CO2? Are they as good as I claim they are? So this is a time study we did, and we went out and collected a whole bunch of samples at Lambert's Run. I think we filled 350 bottles that day, because these were all done every day in replicates of 6, and they were analyzed for all kinds of different things. So day 0 is the day we collected our samples, and that was an analysis in the field. And then on all of those different box days, we came in and we analyzed 6 samples on the CarboQC. They were samples that were held in the refrigerator all this time. So the question is, how much loss did we get of CO2 over that time? And the blue box gives you a 5% loss. So starting with the original concentration and saying, okay, how much is 5% loss? What you can see is in the first 10 days, we had next to no loss of CO2 at all. And we do get more loss as time goes on. Now, the standard holding time for a Shimatsu on this is 40 days, which ends up being important. 80 days is longer than really you'd want to do this. We just thought it would be interesting to collect that extra data point out in the end. So we feel like this method really is keeping CO2 in the bottles very well. And again, each one of those error bars are based on replicates of 6. Okay. When I say amount of CO2 loss, that's just this degassing. I also calculated this as a percent. So same figure on the upper left and the lower right is my amount of CO2 loss over that time of day since sampling. Now I've put a vertical line on day 40, which is the holding time for the standard method. And what you can see is getting up to those 40 days, I'm always less than 6% loss. And really, if I analyze these in the first 10 days, less than 2% loss, which I feel pretty happy with. I feel like, yes, Coke and Pepsi have done us a solid in this case by creating a bottle that works much better for us. Okay. I also want to do DIC this way, that we would be able to collect bottles and bring them back into the lab and analyze for DIC. But this is a trickier problem because if I have a sample and Ben goes out and collects a sample for DIC, and if it's high in CO2, how am I going to analyze that when I bring it back? Because if the pH is high enough, I don't have measurable CO2 I can measure on my instrument. So what we do is we create basically reaction cells where we have these bottles and we prep them for the field. And they contain a little ampule with some concentrated HCl and some ball bearings. We usually put 2 in, not 3. And when we send them out in the field, they're full of deionized water, which gives it a nice little, just enough buoyancy that things don't break as they travel around. You ever had one break, Ben? Camille? Okay, excellent. That's good.
I don't think so. Camille, have we?
No, but I've definitely accidentally poured them out when I'm sampling.
Yeah, you have to be careful when you get out into the field to pour out the deionized water, carefully rinse that bottle 3 times. But doing that as individuals in the field, I think seems to work pretty well. Ben and Camille at least have been very good not breaking the ampules and doing that. We always send some extras just in case. But I think the transport is where we would probably have them broken if we didn't have them filled with deionized water. Okay, so we create this little reaction cell in the field. They get wrapped with electrical tape as well, and then they come back into the lab. So what happens in the lab? I take my bottle and we shake it. So moving from right to left of my bottles, there's the initial sample, comes back from the field. It gets shaken very hard to break that ampule, which takes more pressure effort than you might think. In doing that, we release the acid. The reaction takes place and my pH comes down typically to 1.4 is what we've been seeing in that range. It's definitely less than 2. So I've converted all of my DIC into the CO2 form. I've done that in a contained reaction vessel where CO2 can't escape very well. And now I can analyze it for CO2. So far, this is working pretty well, and we're all getting much, much better at blowing our ampoule shut. Okay, so how well do these hold in the field? So this is a similar figure to the one we saw. The red is CO2. That's the exact same data set you saw on the previous slide. The blue are the DIC samples from that same time study. And what you can see is there is a little more variability in these. But again, I see pretty consistent concentrations over time, particularly in those first 40 days. So how much DIC did we lose in this process? So this is very interesting, this upper graph. So the upper data set on the upper graph, it says CarboQC, they're in gray. That's that CarboQC data set from the previous slide. So the blue data set on this slide is gray on this side, and it's the CarboQC. So we do lose a little bit of CO2 in it. The red, however, is doing the standard method on the Shimatsu. So this is where I said the Shimatsu, the process and the sampling vials do not keep CO2 in. Because I'm working in samples with a very high partial pressure of CO2, I'm losing CO2 in that process. So you can see that DIC on the Shimatsu, by the time I get out to the 40-day holding time, I've lost half of my DIC in the sample. If I look at that percent-wise down below, my CarboQC, I've lost, oh, I forget what the percent is. It's less than like 5%. It's not a big loss on my CarboQC method for DIC, but the Shimatsu may have lost a third of the sample by the time we get to that 40-day holding time, a quarter to a third. So this is, again, my argument that the Shimatsu, if you're measuring DIC on the Shimatsu, but you have a high CO2 sample, you're going to lose it. It's not going to stay where you think it is. Okay, so here's where I've gotten kind of stuck in the recent months, and some people have heard my woes. So if I do this particular process and I'm using acid, so I'm not using that ionic strength adjuster, which in retrospect might have been a mistake, but if I'm using acid in this, I need to adjust my formula a little bit. One is that my pH is going to come down lower in this case. This ionic strength is not as consistent as when I use that ionic strength adjuster. But the other thing is my dilution factor now is a function of the bottle, because not all the soda bottles are the same. We use whatever people donate to us that we get hold of. They're not all the same variety of soda, let alone the exact same size. So we have to account for the volume in every bottle. So let's say I do this, I create my standards in the bottle just like this. And this is what my standards look like, where I have my known DIC on the x-axis. The y-axis is the DIC when we've measured the CO2 in the CarboQC, and I've calculated the CO2 from that. I'm sorry, these are both in terms of DIC, but we're working millimolar, so they're the same in this case. The solid line is just a parity line, which is what you'll see in all these standard figures. So what I see is the amount of CO2 coming off the CarboQC, and what I'm measuring, it's underestimating a little bit my known concentration. So I'm a little concerned about that bias, and I'm a little concerned about what those numbers are. The red symbols on this assume that the CO2 I measure in my bottle is exactly the DIC with the dilution factor, of course. That is, I'm assuming I've converted every bit of DIC into CO2. When I measure CO2, I'm just getting DIC. The problem with this is now this correction between activity and concentration. So if I account for the ionic strength and I make corrections for some of the activity coefficients, I get the blue symbols on this, which are a closer match to the line. So let me take you through the different options on this. So this is our equation again above, and really all of this, the final answer comes down to the gamma CO2. The gamma CO2 governs what we have here, because the later terms in this equation that account for the bicarbonate and the carbonate are mathematically negligible. They don't end up being very important. Okay, so here are some assumptions I can make on the activity coefficient gamma for CO2. First is I can assume gamma is 1. Simplest model, if you want to think about it that way, that the concentration and the activity are the same. The gray dots are on there, and it's off a fair amount. I'm sorry, those are the red dots, The next thing I can use is an ionic strength adjustment for neutral species, and that is an equation out of Stum and Morgan, and it's used for neutral species, and that gives me a gamma CO2 of 0.96. These are the blue symbols, which is a reasonable match. We're getting certainly closer to the line. The third option I have here is use the gamma we've used previously, which we had come out of Freak and Mintech modeling, where the gamma CO2 is 1.09. That's the gray, the furthest off. So the question, what it comes down to is, if the most important factor in this calculation and making sure that our numbers are accurate, the most important factor is the activity coefficient for CO2. However, that's a model value. There are different ways it can be modeled. So the question is, what is the right model and what is the most reasonable model and the most justified model? If I think about this in the sense of the old way we did this, using the Orion ionic strength adjustment buffer, we used a value of 1.09. And again, that came out of, I think we did it both in Mintech and Freak and came out with very similar numbers. What I'm suggesting for this newer method using just HCl is a correction of 0.96. Do we change it? And that's what I've been struggling with lately. Now, when I compare the mixtures, they're pretty different. So if I look at the sample and the Orion buffer together, I get an ionic strength of like 0.3 to 0.4. My final pH is closer to 4. However, when I use concentrated acid to bring my pH down, I have a much lower ionic strength, and that's controlled by the acid, it turns out, and a much lower pH. So is it justified using a different gamma? And I think it is. And it really took me till this weekend to come to terms with it. And I think the reason is, if we think about how a neutral species behaves in solution, a greater than 1 log gamma suggests that we are forcing the gas out of solution. That is, it is a neutral species. And as the ionic strength goes up, it's harder and harder for a neutral species to stay dissolved. So it makes sense I would have a gamma greater than 1. That says log gamma there. Those are actually gammas, not log gammas. I will correct that on the figure before I send this out. Okay. In our other mixture, one, we're at a much lower pH, but we're also at a much lower ionic strength. And I think perhaps that the force to drive the CO2 out of solution isn't as strong because of the lower ionic strength. Could you argue this either way? Yeah, you probably could. And I've tried to go back and sort this through. There is very little good information about how to really calculate a good activity coefficient for a neutral species. That equation in blue on this figure is one of the few. You see it lots of places, but people don't pay much attention to this. I wonder, with all the CO2 injection in the brine world these days, that people haven't paid more attention, but I haven't been able to find it. I'm still looking. Okay, so where does this leave us? Going forward, let's say I say, I'm going to go with that gamma CO2 based on the equation of adjustment for a neutral species, citing Stubb and Morgan, which gives us the gamma CO2. And again, that is correct. It's not a log value, but a true value of gamma CO2 is 0.96. If I use that, I get pretty close to the parity line for my known standards, which is the figure on the left. Pretty happy with that. So the question is, how much? It seems to be bias low. And the fact that it's all low suggests to me there's a real bias there, something systematic, it's not a random error. But the question is, how big of an error is it? Is it a problem, or is it an acceptable amount of error? So this lower figure, I've just given us the known DIC. That's at different millimolars. These are the standards we created. And on the y-axis, when I say loss from known, that is, I said, this is the amount difference from the known standard. So it's basically a measure of the error. And if I look at this percent-wise, at low concentrations, my error may be up to 10% in that range. And at higher concentrations in my DIC, the error comes down. Not surprisingly, we have that larger error in a smaller number. A lot of that's mathematics, some of it's measurement. So it still left me a little nervous. Then I went back and I said, well, let's look at this not in terms of percent error, but let's look at it in terms of absolute measurement of millimolar. And when I look at how much error I have in the millimolar concentration, it's pretty low. So it's between 0.2 and 0.5 error on the millimolar. And finally, this weekend, I went back and I added a bar on this plot, which is the resolution of the instrument. The resolution of the instrument is 0.23. And I think that all of these values are within the resolution of the instrument. So although I think we probably could be a little more accurate, and again, I'm still somewhat concerned about that slightly low bias, I'm not sure that even improving that actually makes us more accurate given the resolution issues. Okay, so Camille, this means that we can start moving forward on your data because you and I have been talking about this. So this is a good thing. But what do we need to do next? I'm still sort of chasing that bias and the residual in this. Things we're going to do. Morgan's going to work with me. We're going to make new DIC standards. I bought brand new solids. We'll get those dried. So we're going to be starting with the very, very fresh solids to make our DIC standards. I also want to do a quick time study on the new DIC standards. We did the time study before based on a field sample, but I'd like to do that at a couple different concentrations of DIC. I have broken down and ordered some Anton Par calibration standards as well, just so I have that check on the data. A couple other things I want to look at. One is the ball bearings. Do they dissolve enough to alter the chemistry? They do dissolve a little bit. And I want to just play with how much metal I can put in that solution. Does it have any impact on the CO2? My guess is it does not, but I can quantify that. And the other is there's a little bit of headspace in those vials because we can't fill the vial completely full of DIC and then blow it. If we then try to melt it, either we end up having problems with hot acid everywhere, or we have problems where the vial gets hot enough close to the acid that I lose some of the acid. So my amount of acid is not the same because I've burned some of it off. So I want to look at that headspace issue a little bit. And again, I don't think either of them are going to be major. Again, remember CO2 is pretty soluble, but those are two errors I know I can quantify in the process, and we'll check some new standards and do a little bit more of a time study. So I still want to do these to clarify, but I think we're pretty much ready to go with the data we have, the stuff that Camille and Ben have been collecting. So just a quick how-to. This is partly for the lab crew, partly just sort of interest. How do we prep these bottles? Dietrich's been doing a lot of this year. We start by adding acid to the ampules. We were using 3 mLs, but we're switching to 2 mLs. The reason for that is we've moved from butane to propane, and propane is much hotter, and we seem to be burning off acid if we fill the vials too full. So we put acid in our ampules, we seal them in propane, let them cool, and then we test for leaks. You can't test for leaks before they cool, or else you turn your little ampule over and the hot acid, or the acid hits the hot glass and they go poof. That's always kind of exciting. Just sort of some QC on the ampules. We let them cool, we test them for leaks, then we rinse them off and let them dry. Then we put 2 ampules and the ball bearings into a clean, dry bottle. We add a cap. The cap and the bottle are numbered together so that they always go together. We weigh that, then we fill the bottle with deionized water and reweigh it. We know that deionized water has a density of 1. And so I now know the mLs in that specific bottle just through subtraction. The temperature of the water, we should use room temperature water. I think that's worth paying attention to. However, it's not a considerable error in this reading. Okay, and all that gets reported. So the prepping of the bottles is not really trivial. This is the kind of data, we have a notebook. This is all we do is write this down, date prepped, the number we put on the bottle and lids, and then we have the mass, lid, ampule, and bearings, and then we have the DI, re-measure the mass, and now we know our grams of deionized water. The analysis, I take my this is my setup where I have my pressurized filling device connected to my CarboQC. I take my cute little soda bottle, I put it in the pressurized filling device. This is after it's shaken up. I should have used a bottle with a broken ampule, and we send that over. One of the things we do check at the end of the waste mixture coming out is pH, partly because waste handling, if it's less than a pH 2, we need to send it off as hazardous waste. If it's more than that, we do not. I also want to make sure nothing strange happened and I didn't end up with some strange reaction in which I didn't get enough or low enough pH. We were measuring specific conductivity as well on these, hoping that would give us an approximation for ionic strength, but it did not give us a very good value, at least not one that we felt we could use consistently. After we do that, we have our data. Now we need to do our final calculation, which we calculate the DIC based on our gammas. And I think we're just going to use fixed gammas for everything. Again, the only one that really matters very much is the activity coefficient for CO2. The others don't make much of a difference, and we're going to go with a constant value in that. And also our bottle specific dilution factor. I use a lookup function that lets me go hunting in the big table of bottles and come back and tell me the volume of the bottle. Whoa, okay, that was whirlwind. I made it in just under an hour, but didn't leave you a lot of time for questions. I realized I didn't do the derivation of that equation. I'm happy to work through that with people if they want to at a later time, but I didn't have my digitizing tablet here today. I actually think those of you who really need it have the skills to develop it. So it might be fun for you guys to try it. I just should, this is one of my, as many of you know, my pet peeve about using the little p for PCO2 for partial pressure, which is incorrect. Little p to me designates a negative log concentration, which is why that concentration is a big X below. I realize it's propagated through the literature differently, but I encourage all of us to remember that a partial pressure is a large capital P, according to the American Chemical Society. And also encourage people, it's better to work in millimolar oftentimes, just to make life simpler. And you can see the CarboQC out on its field site with its special little umbrella from Hank, staying safe and sound and dry. Whew. Okay. The story of the CarboQC. There you go. What we do, what we've been doing, where we're headed. And I guess I'd love to hear some comments or questions. Thanks, Dorothy.
Yeah, lots of information there, Dorothy. I have a question.
Yes.
So you were initially using one acid ampule in all your sort of scoping experiments, right? And you said you've and your comment was that it was the acid that controls the ionic strength.
Excellent. Yes.
So now you're,
if we move to 2, do I still have that answer? I'm going to calculate
Yeah.
that and find out.
yeah. I mean, just need to pay attention, I guess, as you
Yeah.
move forward into the new protocol. And I have to admit, I'm surprised that the specific conductance measurements weren't more comparable to the ionic strength you were getting by other means.
Yeah. I'm not sure I know the answer to why, whether it was instrumentation or the method.
But so let's say you changed to these 2 ampules of acid. Was that what the change is going to be? Or was it changing from 3 mils to 2 mils? I'm sorry, I've lost track of.
My plan was we were going to switch from 3 mils to 2 mils, which is absolutely critical for that ionic strength. So we might want to think that through a little bit more. I think
So
is only about 10 ampules in.
But for the 3 mils, so you calculated ionic strength from?
For the standards, yes. So based on the solution chemistry of the standards,
Okay.
I've calculated the ionic strength on that.
Well, so you just need to check it again, and it might work well in your favor if it's a little less concentrated. Yeah, I was looking at my shelf. My Sturm & Morgan must be on a different bookshelf. I'm going to look at that neutral species activity coefficient equation, because it's definitely not the salting out sort of approach that
Right.
Mintech used to get the activity coefficient greater than 1. I'm just curious.
Yeah. So this is
So
my
if
other favorite book on CO2.
Oh yeah. Yeah.
By Butler, which is carbon dioxide equilibria and their applications. But again,
Great book.
even in this one, it's a very rough approximation for how we will handle an activity coefficient for a neutral species. And some textbooks just say, oh, it's 1.
Well, yeah. but I'm trying to figure out if your ionic strength's a little bit lower with the 30% reduction in the amount of acid.
Yeah.
Does that push the activity coefficient closer to 1? It
That's
might.
a really good question. And, you know, Dietrich and I were in the lab last week filling ampules and trying to seal them, which is one we thought we'll go with is 2 mLs. And I never thought about the fact that it's going to adjust the ionic strength. So I'm going to do that calculation before we made a final decision on which to use. Got that, Dietrich?
Yeah, in that case, should I hold off on ampule making for the next couple of days, or?
Yes. Yeah.
Okay, sounds good.
But honestly, an activity coefficient of 0.96 is really close to 1 anyway. And all your, I don't know, errors seemed like they were in the 10% or less range, which is really good. Like you say, it's the same as your analytical error.
Yeah.
It all looks like you're headed in the right direction to me, but I would recalculate that ionic strength with the changed amount of acid.
Oh, I'll do that. Absolutely. No, that's a good point. And I think you're right that potentially could throw it. We may decide not to go to 2 mLs.
I don't know.
But that is a calculatable answer. Other questions, thoughts? I mean, really, when it all comes down to what we're really looking is, do we use a correction factor of 0.96 or 1.09? They're awfully close. And in either case, I end up with a little bit of a low bias, but it does make a bit of difference in the error. But I think that it's not, I think from an interpretation standpoint, it's an acceptable amount of error. I've convinced myself of that this week.
And Dorothy, for this summer, with the work that Dietrich is going to be doing, we will have a lot of paired DIC and water samples and the whole cation anion balance. So that might be a good data set to play around with.
Absolutely. Yeah, that'll be helpful because then we can
Ionic
do
strength.
real true ionic strengths. We could even choose for those samples to do a sort of special adjustment on the calculation that leaves us where we're a little more accurate.
Yeah, with the full compositional information, you could calculate ionic strength and make a unique adjustment to that sample. But it's still going to be a small percent adjustment.
Yeah, yeah, between 0.96 and 1.09. Yeah, that'll be fun for Dietrich to work out. So just
So, yeah.
Ben's got a research project where they're looking at CO2 in a treatment system, and Dietrich's going to work for Ben this summer and collect data for his master's while helping Ben out on his consulting project on this question. So
Yep. We're adding CO2 to limestone treatment systems to boost alkalinity generation. So
it sounds
beautiful
almost like
DIC mass balance. Dietrich, you're gonna love it. The DIC mass balance.
I'm sure that in due time I'll be able to do it in my sleep. I'm sure of that.
I have one more question, Dorothy. So the major correction here is the CO2 activity coefficient. You said the temperature corrections for K1 and K2 are relatively minor, like
yeah,
they don't matter. Okay.
they don't, and we make them. So
Okay.
I always make the corrections, but the amount of change based on those is not that big. Plus, keep in mind too, they're in the terms for the bicarbonate and the carbonate anyway, which are small terms to start with.
Right.
And Morgan, I'm sure you're happy to see your friend, Euripides. Morgan worked in Neil Plummer's old lab at USGS, Janet. I don't think you knew.
Wow. Wow.
Yep.
Trained by the best.
For sure.
Yeah, no, that
Absolutely, for sure.
Okay.
What? I have a very different question, and there's probably a really short answer. Do you ever have any indication that you have organic carbon species? Is there ever any chance that you have significant amounts of DOC?
I don't know that it would show up in the method because
No, probably wouldn't. But
typically what we find in these really high CO2 systems, it's hard to measure the organic carbon. Now we've done that. And what we do is we take our ampules and we open them and we add acid and we let them degas. So we try to get all of the DIC out. first. And then we analyze for TOC, but it's typically orders of magnitude less in these systems.
Okay, yeah, that makes sense. Yeah, I was just curious. Thank you.
Yeah, no, and in fact, I think I've seen a lot of calculations where people have tried to calculate DOC in these waters based on the standard method. And because they're not getting rid of the they're not getting rid of the DIC effectively enough, I think their numbers are biased. I know, Ellen, you were nodding, like you guys have done some of that too. You have the same instrument.
Yeah, it does damage to the Shimadzu too. So you gotta
Oh,
watch that. And yeah, we've had some interesting, but I mean, there is DOC. I actually thought it would be even lower dissolved organic carbon in there, but there is some, but it's difficult to measure accurately. And we get huge error bars for totally different reasons than the CO2 degassing error bars.
Yeah, so there's ways you can work around that and get some numbers, but you have to pay attention to it, make some conscious adjustments on the method. So. Okay, and Dietrich and Morgan, you guys are going to be the ones using a lot of this in our lab. You'll want to make sure that you could derive that DIC calculation. My guess is after aqueous geochem, neither of you would have much of a struggle doing that. But I'm happy to run through that with you at some point too. All you need to do is start with your DIC mass balance and then solve for the bicarbonate and the carbonate masses based on the activity of CO2. It's very similar to some things you did in class. So I know you can do it, but I'm also happy to help if you'd like. Okay. We all good? Thank you guys, and thank extra people. Janet, I really appreciate you coming. I knew you'd have some thoughts on this.
No, very interesting. Thanks for inviting me.
Dr. Geochemistry, as we think of you.
Right.
What I've looked up to my whole career, I will say. So, and Ben too, I'm glad you could come because I know you're going to be utilizing the method quite a bit coming along. So, and Ellen, here's your data.
Yeah, I really need to do something with that. All that does is make me feel guilty. It's not published.
Yeah, that's easy. Okay, thank you, everybody.
Thanks,
And
Dorothy.
I'll see you all
Thank you, Dorothy.
another time.
Thank
you.
you.
Thanks.